Hello, guys and gals. I hope everyone had a wonderful Easter. We have a test this week, and this is our last section for this unit. So let's look at section 4.6, which are not invoices, inverses of functions. Oh, there it is. I should have paused. Inverses of functions. So let's look at the definition of inverse. It says, let R be a relation. The inverse of R, denoted R to the -1, is the relation defined by switching the first and second coordinates of each ordered pair that is an element of R. So in other words, when you have a coordinate point, a set of coordinates, you have the first number is always the X, and the second number is always the Y variable. So when you find the inverse of a relation, you would switch those and let your X's be the Y values and vice versa. For example, if we have letter R, and these are the three coordinates that make up point R, or these are all of the coordinates of R, then if we are told to find the inverse of R, all we're going to do is simply switch the order of the coordinates. For example, instead of 4, -1, I would write -1, 4. Instead of -3, 2, I would write 2, -3. And instead of 5, 0, 5, I would write 5, 0. So these coordinates are the inverse of our original set of coordinates. All right, so I'm sending y'all this PowerPoint, so make sure you read all of the slides. You guys take time to do that, please. All right, so then basically when you find the inverse of a relation, it always is going to be an inverse over the line y equals x. So if y equals, basically remember how to graph a line, our y-intercept would be 0, and then our rise and run is both 1. So up 1, right 1, up 1, up 1, left 1, right 1, up 1, right 1, up 1, so on and so forth. So along this line, our points, our coordinates are going to be mirror images of each other. For example, let's look at this point right here. So this original coordinate, if this red dot was our original coordinates, this would be at -1, 4, -1, 4. So the inverse of that would be 4, 1, or excuse me, 4, -1. So that's where we find this blue line dot right here. So +4, -1. So these are inverses of each other. They are mirror images over this line, which is y equals x. All right, what about point R up here? So the original coordinates for point R would be -3, 2, -3, 2. So the inverse of that would be +2, -3, right here. +2, -3. So these are mirror images of each other across this line, y equals r. And then, of course, we have one more example. All right, it says determine the inverse of each of the following relations. Then graph each relation and its inverse and determine the domain and range of both. So basically this is y is equal to x squared. So we would literally switch the order of x and y. So instead of y, we would write x. Instead of x squared, we would write y squared. Okay, so if I had a coordinate, or maybe I do. Do I? No, I don't. Anywho. So if I take this original and I plug in values for x and y, if I let 0, let's say I have x equals -2, 0, and +2. So -2 squared is +4, 0 squared is 0, and 2 squared is +4. So I would get a parabola like this. Well, then when I switch these, And this time, if I let y equal 4, let's see, 4 squared, x would be 16. What if y were 2? 2 squared is 4. What if y were 0? 0 squared would be 0. What if y were -3? Well, -3 squared is +9. So when I graph these, I actually have a picture of it. And of course, you can always look this up on Desmos. I'll get to the picture in just a second. But here it says, in this problem, r is described by the given equation in x and y. So basically, that's what I did. I took the original coordinate and I switched the letters right there. So instead of y equals x squared, the inverse would be x equals y squared. So in our original equation, our domain is going to be any real numbers, any real number we could plug in for x, any real number. And then the domain, the range is going to be from 0 to infinity, because anytime you square a number, you're going to get a positive answer. So we couldn't have an answer less than 0. 0 is the smallest y value we would have. So then when we write the inverse of r, do you notice that the domain becomes the range and the range becomes the domain, because we're switching everything, right? And let me show you the graph of both of them. So the blue was the original, y equals x squared. And then we switched x and y, we get the red. And so once again, these are inverses of each other along this line, y equals x. These are the inverse of each other, right? It's a mirror image over y equals x. Note that the shapes of the graph of the relation and the graph of its inverse are the same. The shapes are the same. It's just a mirror image flipped over y equals x. Now, we are faced with another example of the reuse of, my face is in the way, of the notation. Note that f to the -1 does not mean 1 over f when f is a function. We use an exponent of -1 to indicate the reciprocal of a number or an algebraic expression, but when applied to a function or a relation, it stands for the inverse relation. So if we were talking about 5 to the -1st power, we would get this answer. But this is, it looks like it's a similar notation, but it means something completely different when it's applied to a function or a relation. The -1 just indicates that we're talking about inverse. So be careful with the use of that exponent of -1. All right, so when we started doing functions, last unit, I suppose, we talked about how to identify if a set of ordered pairs, which are relations, are functions, and we talked about the vertical line test. Remember that? We said that this passes the vertical line test, so on and so forth. So now we're going to talk for the first time about the horizontal line pass. It says, let f be a function, any function. We say that the graph of f passes the horizontal line test if every horizontal line in the plane intersects the graph in no more than one place. If f passes the horizontal line test, then the inverse of f is also a function. So basically what this means is that any set of ordered pairs is considered a relation, but it takes a special circumstance to figure out if an inverse is a function. The inverse of is an actual function, okay? So the function f is 1-to-1 if for every point of distinct elements, we have the function of x of 1 is not equal to the function of x of 2. This means that every element of the range of f is paired with exactly one element of the domain of f. So in other words, we're trying to see if the inverse if a function passes the horizontal line test. If it does, its inverse is a function. If it doesn't, its inverse is not a function. Even when a function f does not have an inverse function, it always has an inverse relation. So very broad definition here for the word relation. Functions have a much more limited definition. All right, so basically, what does all this mean? So it means if you have something like this, so basically when I look at that in my brain, I'm thinking y equals the absolute value of x. I want to know if this is going to have its inverse as a function. So guess what I'm going to advise you to do? I'm going to advise you to take the original equation and plug it into Desmos. So I'm going to stop sharing here. I'm going to find Desmos and I'm going to type, where did Desmos go? Let me try it one more time. Let me try it one more time. There it is. All right, so I want to type in y equals the absolute value of x. Now, hopefully you can see my graph over here. I thought I could scoot it over. I'm sure I don't know how to use this. There we go. Now, if I was going to make a horizontal line, I don't think I can write on this. I can't. So imagine me making a line horizontally across this graph. So do you see how my horizontal line would cross this graph in two places? So I'd go 1, 2, I just passed it, 2 places there. If I came up here and did a horizontal line test, it would go through my graph twice, 1, 2. That means it failed the vertical line test, which means its inverse is not a function. So if you're not sure, all you got to do is pull up Desmos. You need to graph your original equation, and if it does not pass the horizontal line test, then it says it doesn't have an inverse function. Okay. So I just proved that that one does not pass the horizontal line test, which means it does not have an inverse function. It says the function f does not have an inverse function, a fact demonstrated by showing that its graph does not pass the vertical line test. So basically they took 2 integers, they plugged it into the original equation, and they said that that has the y value of -x is going to have 2 different places where it is crossed on your graph, so it does not pass the vertical, oh, here it is right here, the horizontal line test. So this is what Desmos showed us. And once again, I can show you that we do not have a inverse function here because it fails the horizontal line test. All right, so here's 2 others. So we're going to pull up Desmos, we're going to plug it in, and I'm going to show you guys what I'm trying to say in kind of a complicated way. All right, x plus 2 to the 3rd power, x plus 2 to the 3rd power. I'm going to try to remember this. Okay. All right, y equals x plus 2 to the, I got to use my little caret, to the 3rd power. And then it said something else, didn't it? Like plus -2, I think, something like that. I don't remember. All right, so I got to scroll out. I got to get down here a little bit. And I'm going to scroll. Nope. Come here, guy. All right. I just wanted to see it a little clearer. Now, do you see that this line, this red graphed line, or it's not a line, but this red graph would pass the horizontal line test? If I made a horizontal line anywhere on that graph, it's only going to go through the graph one place throughout the whole graph, which means that this equation's inverse has an inverse function. This equation has an inverse function. Okay, so let me go back to my PowerPoint. All right, so this this graph is also very, very similar. So if I graph both of the, I think I actually plugged in x minus 2 to the third power. If I typed in Desmos x plus 2 to the third power, I'm going to get very similar graphs, and I would see that both of them pass the horizontal line test. It says the graph of G is the standard cubic shape shifted horizontally 2 units to the left. We're talking about letter A on the previous slide. You can see this graph passes the horizontal line test, so G has an inverse function. And there it is again. So once again, you see all these dotted blue lines. It means we're doing the horizontal line test. It passed there, it passed here, and also passed there on the bottom part of the graph. So that means it has an inverse function. Algebraically, any two distinct elements of the domain of G lead to different values when substituted into G. So G is 1-to-1, and hence, I love that word, has an inverse function. Okay. All right, so I'm sending you guys this. Make sure you read through these slides, okay, guys? Find the inverse of each of the following functions. So the first thing I would do, first of all, I would determine if it has an inverse function. I would plug it into Desmos, and I would see if it passes the horizontal line test. If it does, then I'm going to solve it and figure out what the inverse is. So I always change this f of x. I'd go ahead and change it to a y. Y equals x minus 1 cubed plus 2. So that's the original. Now to find its inverse, what you're always going to do is change your y to an x and your x to a y. So then after you change, so let me make some notes here, change x and y. Then you're going to solve for y. After you change x and y, step 2, you're going to solve for y. So first thing I'm going to do is get rid of this plus 2 by subtracting 2 from both sides. So I'm going to have x minus 2 is equal to y minus 1 cubed. Now the only way to undo cubing is to find the cubed root. So I'm actually going to find so I could write finding the cubed root of x minus 2 as this. Or another way of finding the cubed root is actually raising this to the power of 1/3. These two are equivalent. They're exactly the same thing. Okay, so just, I don't know, to me, using the exponent's a little more clear right now. So I'm just going to show that I'm going to raise this to the 1/3 power, and I'm going to do that on this side, and that's the way, not a 2, a 3. That's the way I can eliminate that exponent, because if I multiply straight across, I'd get 3/3, which is 1, and anything to the first power is simplified, right? So I have x minus 2 raised to the power of 1/3. I got rid of that exponent of 3, and now I just have y minus 1. And remember, what I'm trying to do is get rid of everything on the side with y. So the last thing I'm going to do is add 1. So I can write this 2 different ways. I could either write x minus 2 raised to the 1/3 power plus 1 equals y, or I could go ahead and put x minus 2 and the little radical plus 1 equals y. I'm 95% sure Hawks would take both of those answers, either one of those answers, because they are equivalent. Okay, they mean the same thing. All right, so what did we do first? Well, I guess the very first thing is we wrote f of x as y equals. Okay, so then what did we do? We changed, we exchanged x and y. We traded their places. And then the last thing we did was solve for y. That's what we did. Oh, I see this now. All right, so they wrote it as a radical. So they did exactly the same thing I did. So the first thing you want to do is write f of x as y equals, bring everything else down. Then you're going to, I was about to say, then we're going to exchange. Anyway, they didn't change their places, did they? Well, I guess they did at the end. But anyway, we got the same answer, right? We got the exact same answer. All righty. Find two suitable restrictions of the domain. Hold on, let me go back. All right, guys, just make sure you read through these, okay? Look at the solution slide. We talked about, you know, happy parabolas, sad parabolas, so on and so forth. All right, so it says find the inverse of restricted domain function. So first of all, this is a parabola, so it doesn't have an inverse function, right? So you guys read through those. So even if it doesn't have an inverse function, they all have inverse relations. So like I said earlier, the definition for relations is much broader than the definition of functions. All right, and then once again, we see this is the blue and the red are mirrored images of each other over the line y equals x. All right, let's do some more examples. All right, there's another example of a mirror image. All right, here we go. It says find, so these are Hawk's questions. I got these from Hawk's, very, very similar questions than these. It says find 4 points contained in the inverse. So this is our original equation. So what am I going to do first? I'm going to exchange x and y. And then my next step is to solve for y. So I exchanged x and y first, and now I want y by itself. So the first thing I'm going to do is add 3 to both sides. So I have x plus 3 equals 3y. And then the opposite of times 3 is divided by 3. And this is gone. So the inverse of this is x plus 3 divided by 3, the whole thing divided by 3, and that is the answer. And remember, you can't cancel out these 3's because that plus sign holds this whole top together. So don't try to cross out those 3's. You're not allowed to do that. Oh, so find the domain and range of the inverse. So remember domain and range. So if I graph this, I would get a straight line that goes kind of like this. We talked about y-intersect, and we talked about a straight line. So we would go up 3, right 1, up 3, right 1, so on and so forth. So the domain would be, our line would go in both directions forever. So our domain would be negative infinity to positive infinity. Whoops. The domain would be negative infinity. Oh my goodness, what is wrong with me, you guys? I'm sorry. The domain would be, third time's a charm, you guys, negative infinity to positive infinity. And then the range, would this ever stop going down, or would this part ever stop going up? No, it would also be from negative infinity to positive infinity. So the inverse, we're going to make the domain the range and the range the domain. So guess what? They're going to be the same. But so basically, I guess really a better definition for domain would be all real numbers. So if we, you know, found the inverse, we would say the range is negative infinity to positive infinity, and the domain are all real numbers. Those would be just the opposite of each other. All right, so here it says find the formula for the inverse of the following function. So first thing we're going to do is replace a of x to y equals the cubed root of x plus 2. That was step 1. Step 2, you exchange x and y. And now you want to solve for y. So y is stuck under this radical for now. So what we can do is subtract 2. So we're going to do x minus 2 equals the cubed root of y. Well, how do you get y free? Well, the only way to get rid of the cubed root is to cube this side, which cancels out the cubed root. Well, you can only do that to one side if you do it to the other. So now the cube root and exponent of 3 cancel each other out. So what does y equals? Y equals x minus 2 cubed. That's what y equals. Okay, and first of all, you would need to put this in Desmos and make sure it's a function. Make sure it passes the horizontal line test, and it does. I checked it out. All right, so what about the one on the right? So first thing I'm going to do is write a of x as y equals 3x plus 2. Basically, it's asking what's the cubed root of this 1/3. So now, after we've made a of x a y, now we're going to exchange x and y. Now the third step is to solve for y. So we have to get rid of this 1/3 exponent. Well, the only way to get rid of a 1/3 exponent is raising it to the third power, because now if I multiply 1/3 and 3/1, I get the exponent of 1, but I have to do that also to this side. So now I have x to the third, or x cubed, equals, we got rid of that exponent of 1/3. Now y is free. We have to get rid of minus 2 first. So we have x to the third minus 2 equals 3 times y. And then finally, the opposite of times 3 is we're going to multiply this whole side by 3. So what does y equal? Y equals x to the third power minus 2 divided by 3. This is the inverse of this. Okay, I hope that makes sense. All right, let's do another one just to be sure. We're going to write the inverse. So first of all, I look at Desmos to see if its inverse is a function, and it is. I checked it out already. So now I'm going to write y equals the 5th root of x minus 4. And now I'm going to exchange x for y. And now the last step is to solve for y. Well, y is stuck under this radical, so the only thing I can do for now is add 4. So I have x plus 4 is equal to the cubed root of y. And the only way to get rid of this radical cube root or 5th root of y is raise it to the 5th power. You can only, whatever you do to one side, you must do to the other side. So now these two things cancel. So what does y equal? Y equals x plus 4 raised to the 5th power. And that is the answer right there. Okie dokie. All right, now this is a question from my Open Math. The question is, are the following functions inverses? Well, one thing I could do, I could go to Desmos. I could plug in this first equation. Then I could plug in the second equation and make sure if I use that y equals x line, remember that one? Make sure they're mirror images of each other across that x equals y line, or y equals x, I should say, same thing. And that would prove it graphically that they're inverses of each other. Okay, so we can do that if you want to show up for class and you want me to show you examples of what I'm talking about. But I think if you guys just put them into Desmos, you can see what I'm talking about. So the other way to prove it is algebraically, is to make sure when I take the original equation and I switch X and Y and solve for Y, does that equal this second equation? Well, let's see. So we're going to take our original. All I'm going to do right now is exchange f of x for y. So y equals 3x plus 5. That's our original equation. So now we're going to exchange x and y. So I'm going to write x equals 3y plus 5. And now I'm going to solve for y by subtracting 5 from both sides. So then I get x minus 5 is equal to 3y. And then what's the opposite of times 3? It's divided by 3. And I want to know, does the other equation say that y equals x minus 5 divided by 3? Well, it's super close, isn't it? But the answer is no. They're not inverses, because x divided by 3 minus 5 is not the same thing as x minus 5, the whole thing, divided by 3. So this answer is no, because they don't match exactly. All right, let's look at another one. Oh, I thought I had an example of one. All right, but I thought I had grabbed an example of one that was, but I guess I did not. But hopefully that you know, you guys are, hopefully, well, I don't know why I can't speak. I hope that was enough examples for you guys to understand what's going on. Most of you are, y'all just rarely have questions. A lot of you come to the meetings and you're like, I'm done. Is there anything else? That's so great, because I've had students in the past that really struggle, but you guys are doing so great. But anyway, make sure you come to class if you need me. So this class is for Monday and Tuesday, Monday, Wednesday, and then Tuesday class. And then on, I know you guys have a test on Wednesday and Thursday. It's 2 separate classes. And if you will come to class, I'm going to have a live review of the most missed questions from last semester. So it's up to you. You have your choice of starting your test during the day. I know, especially for the Thursday class, or is it the Wednesday class? I don't remember. One of you, your teachers allow you to start much earlier in the day. It's totally up to you. You can go ahead and take the test, and then you don't need to come to class. Or you can wait till after the review with me, and then you can start your test after that. So completely up to you, but that's live on Wednesday and Thursday at 6 o'clock. All right, you guys, I will see you all in either Monday, Tuesday, sometime. I'll see you later. Y'all have a great day.